Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Now that we've learned about the physiology of the human hearing organs, we'll learn about the human hearing sense.
So to get started, let's review what we learned in the last video. We learned that the auditory system, the human ear, constitutes outer, middle, and inner ear regions. The outer ear collects sound to the eardrum. The middle ear, it impedance matches between the eardrum and oval window. This enhances energy transfer. Whereas the inner ear converts waves in the cochlea to electrical stimuli in the brain. The goal of this video is to learn more about this final process. If the cochlea was unwrapped, we would find that a segment divides the scala between that of the spiral lamina and the basilar membrane. So we had before our cochlea in a shape with a coiled structure. And at the beginning of the oval window, we found that there is a membrane that separates everything. Part of it's called the spiral lamina, and the other part is called the basilar membrane. These are separated. Basilar membrane. Pressure waves that occur in the scala result in traveling waves along the basilar membrane portion. The basilar membrane is what supports the hair cells. These are micrographs of hair cells shown in two different views. One when they're shaped like a V, which is the orange square example, and one where they're shaped more in a straight line, that's shown in the green square example. The waves travel along the basilar membrane, but what's unique about this is that because the basilar membrane is short at the base near the oval window, the membrane is stiff at this location. What this looks like when you unwrap the cochlea is that the spiral lamina and the basilar membrane differ in their widths along the cochlea from the base to the apex. We have the apex at the back, which is the back end of the cochlea, and the oval window at the front end. The top part is the spiral lamina. The bottom part of this sketch is the basilar membrane. Because the basilar membrane is short or not so wide at the oval window side, this side of the cochlea is stiffer than the side at the apex, which is softer. The membrane is softer towards the apex. This has important implications for how frequencies are registered in the cochlea. The location along the basilar membrane where this waveform creates a peak of response depends on the frequency. Specifically, what we have is that with the basilar membrane, it is broader towards the apex side and narrower towards the oval window side. And this is our basilar membrane. This means the waves that can fit, in a sense, across the basilar membrane towards the oval window are of smaller wavelength, so they have higher frequency. On the other hand, the waves that can fit across the basilar membrane towards the apex of the basilar membrane are of much longer wavelength. So these waves have a lower frequency. This is again due to the fact the basilar membrane is soft towards the apex and stiff towards the oval window. So the frequencies that can be registered by the basilar membrane vary from about 20 Hz to 20,000 Hz. And this means that the higher frequency limit of human hearing, 20 kHz, is registered towards the oval window side, whereas the lowest frequency limit of human hearing occurs towards the apex side of the basilar membrane. So, let's summarize what we know about the sense of hearing. Acoustic pressure waves are collected by the outer ear, and this causes the eardrum to vibrate. The eardrum then causes the middle ear ossicles to be activated, and the muscles in the middle ear help impedance match to increase the efficiency of energy transfer between the outer and inner ears. The oval window then begins to vibrate, caused by the stapes, and this creates pressure fluctuations in the inner ear scala. The traveling waves then develop along the basilar membrane, cause different regions of the membrane to resonate based on the frequency and stiffness of the membrane, and this then deforms the hair cells and stereocilia that trigger electrical impulses to the brain, which registers sound. This is our sense of hearing and the mechanisms involved in achieving it. It's important to recognize, though, that the cochlea is not just a passive object. The cochlea is an active amplifier. The outer hair cells have motility that are nervously driven, in other words, electrically driven by the brain. This mechanism amplifies soft sounds to help us distinguish differences in frequency as well. This is demonstrated by the graph on the right, which is measured from a chinchilla that has a very similar cochlea as humans. What we see is that when the sound levels are low, the amplifier in our cochlea increases the gain above levels of 1, helping us better recognize low amplitude sound. Whereas when the sound levels increase, such as to 80 and 90 decibels, the gain may actually be less than 1, causing a reduction in sound level. PM refers to post-mortem, indicating that for a purely passive cochlea, there is no capability to result in gain. Amplification is needed because our day-to-day sounds range over many orders of magnitude of acoustic pressure. And we often use this type of dB or decibel logarithmic scale to distinguish acoustic pressure changes. In other words, a 20 decibel change is actually 10 times acoustic pressure magnitude. We recognize this type of amplitude sensitivity in what are called the equal loudness contours. Based on the low efficiency of acoustic energy to the oval window and through the active cochlea, subjective loudness of sounds varies based on the frequency and amplitude. This plot helps us understand this. It's shown in terms of phones or fons, which are a perceptive quantity of loudness. This plot shows, for instance, that at 1 kilohertz, we recognize a 40 decibel sound as actually being 40 decibels. But if we then took that 40 decibel source and then listened to it at 100 hertz, we would have to actually crank it up to 62 or 63 decibels to register the same perceived loudness. So these curves demonstrate amplitude and frequency sensitivity of the human hearing sense. For instance, as we go up to around 80 decibel source, at 1 kilohertz, we'll hear it as being at 80 decibels. But at 100 hertz, we need to crank it up to about 91. So instead of a 22 or 23 decibel change at 40 decibels, we need only a 10 or 12 decibel change at 80 decibels. This is a frequency and amplitude sensitivity due to the active cochlear amplifier. But there are other ways that our brain is triggered to hear. We don't necessarily need sound propagating through the outer ear and middle ear into the cochlea. The cochlea is actually held in bone, and bones can vibrate. The vibration of this temporal bone can shake the cochlea, which also is a means of causing traveling waves along the basilar membrane. Audiological exams test both the airborne and bone conductive sound. And the reduced hearing by airborne compared to the bone might actually be an indicator of middle ear damage or ear canal issues. You're also able to find a wide variety of bone conduction headsets for listening to music, especially if you're doing an outdoor activity where you need to use your ears for quality hearing, but would still like to enjoy music, such as for road cycling. Let's summarize what we have learned. The sense of hearing is caused by electrical stimulation in the brain, in the auditorial areas of the brain. And it's the cochlear nerve that triggers this sensation, and this is stimulated by deformation of the stereocilia in the hair cells. Airborne waves from the ear canal and elastic waves through the temporal bone stimulate the stereocilia. And waves travel further along the basilar membrane for low frequencies and travel less for the high frequencies. And the cochlea is active, and this partially regulates the amplitude of deformation of the stereocilia, which is one means of protecting our hearing over the long term.
That's it for this video. Now that we've learned about the hearing sense, in the next video we'll learn about how hearing may be compromised and how we evaluate hearing health.